last time we left off, we came up with these formulas for figuring out how to replace a distributed load with a single force acting at a single point. So we're going to look at this problem, and I didn't want that backslide. Let's go back. So one of these is covering up the other. Come on, there it is. Okay, just look at this portion here. This is our problem. 0 to 2 meters. W is 60x squared newtons per meter to a maximum of 240 newton meters. And dA is W dx. Here's dx here. Here's distance here. Okay. So the force is just the sum over is the area under the curve. 0 to 2 meters, 60x squared dx. And doing your integral calculus, x cubed over 3, that would be 8/3 times 60, which would be 160 newtons, right there. Now, to get where it acts, you have to do x times w times dx. 60 x4 over 4 between these limits. So that's 16 over 4, which is 4 times 60. And that'll yield 1.5 meters. Or excuse me, I forgot. The denominator has the force. Moment divided by force gives you the distance. Replacing a force in a perpendicular moment with a single force acting at a particular distance. Well, this is the distance right here. Okay. That should be it for this problem. Let's take a look at this one. Now, there's a couple ways to go about this. In the back of your book and in appendices that I've attached from a different book, Bedford and Fowler has a couple appendices that have a lot of these formulas for the different types of distributed loads. And we can break this down into two pieces: a triangular upper half and a rectangular lower half, F1 and F2. We will discover x1 is 1/3 of the total 9 feet. We will discover x2 is 1/2, which kind of makes sense, because the 1/2 especially makes sense, because you have about half of the force acting up to halfway and half of the force acting the other half. So the centroid being the center of the rectangle makes good sense. Kind of fits our intuition. And of course, F2 is the area of the rectangle, 50 times 9, or 450. F1 is half the area of the rectangle, 225. Okay. And now, x1, 3 feet, x2, 4.5 feet. We get the 1/2 and 1/3 from a table of results. Total force being the 225 plus 450, and the x bar given by this equation, x bar times the total force, is going to be the individual force times its distance plus the individual force times this distance. And we're in the foot-pound system, so x bar would be in feet. Okay. I can work this out in my I just worked this out in my head. I just took a moment to work this out in my head. Here's another way to approach it. Two triangles. So a third of the distance of the base of the triangle um, from the second from the from its perpendicular side. So this is 1/3 of the distance between here and here. 3 feet here, so x4 is 6 feet. x3 is going to be 3 feet, just like before, but it's going to be twice as much because the triangle is twice as big as what we had before. Twice as big as this triangle. But the location of the center is going to be the same. 3 feet and 6 feet. And then we can, same calculation, we figure out that x bar equals 4 feet. So let's run through that though. I want to run through that by hand one time. So we can write down W3 being this, check, and that is this height. This is W right here. W goes from 100 at x equals 0 to 0 at x equals 9. And you can check that this will make that true. It's a linear equation. So 100 when x equals 0, 0 when x equals 9. And just integrate it, which is what this is right here, which is a pretty easy integration. 450 pounds, which is exactly what you expect. Now, let's do the integration of xw3. Now we've got the integral of x times w dx, and 100 times 9 is 100. This guy right here, x dx. There's that. Minus 100 over 9, x times x is x squared dx. So we got to solve this. So moving down from up here to down here, we can write down the integral xw dx is going to be 100 x squared over 2, evaluated between 0 and 9. 100 x cubed over 3, evaluated between 0 and 9. Now we just substitute the 9 in and crunch the numbers. Okay, let's wrap this problem up. The integral x w dx 100 x squared over 2 integrated with the limits of integration 0 to 9. Minus 100 over 9, x cubed over 3, limit 0 to 9. Crunching the numbers. I went to my calculator for this. Let's just go through that. So 9 squared times 100 divided by 2. That's this one right here. 9 cubed times 100 times negative 100 divided by 9 times 3, the stuff in the denominator, yields negative 2750. The first one yields 4050. The difference is 1350 out of the calculator. And then divide that 1350 by 450, you get 3 feet. Okay. That should do it, folks. So this demonstrates, I wanted to go through this once just to show you that the triangle, the x bar of a triangle is a third of the base from the big side, or a third of the base from this big side, 1/3 of the distance. Okay, let's move on and end the slide, end the show.